Hi, my name is Andrew Swanson. I'm a developer evangelist for Oracle Database. Today I'll be talking about Oracle Database transactional event queues and event streaming systems. Oracle Database transactional event queues is a high throughput event streaming system that runs within Oracle Database. Now, what exactly is an event streaming system? You can think of this as a service or set of services that facilitates communication between systems, acting as an intermediary for message exchange. Primarily, event streaming systems function to act as a hub for asynchronous service-to-service communication, where event producers write messages to the system and event consumers read messages. Event streaming systems enforce conformant message formats, route messages within the system, and make different guarantees about message delivery, such as at least once delivery, at most once delivery, and exactly once delivery. Within the system, messages are replicated onto persistent storage, ensuring availability in failover scenarios. By definition, event streaming systems should be highly scalable with efficient throughput of up to 1 million messages per second or more with varying payload sizes. There are many different implementations of event streaming systems on the market today, with Oracle Transactional Event Queues being one of them. When and why would you want to use an event streaming system? To understand this, we'll contrast synchronous communication of protocols like REST or gRPC with the asynchronous communication protocol of event streaming systems. Synchronous communication is highly effective for stateless services that are consumed by external clients over the internet. Typically, these synchronous services are tightly coupled with participating services that must be available for the duration of the client request. Due to this coupling, synchronous services are more challenging to scale, and failures may lead to a cascading error scenario and a large blast radius. For example, if one synchronous service in a request chain fails, it's likely that the entire request will fail and the client will receive some form of an error. In comparison, event-driven architectures use asynchronous communication, where each service either consumes or produces a message from the event streaming system. This asynchronous communication model allows services to be decoupled and more resilient when encountering delays or upstream service failures. Additionally, by being decoupled, these services are more scalable and retriable. However, implementing an event streaming system adds an additional layer of complexity to your architecture and can be more complex to implement, monitor, and manage. The benefits and drawbacks of asynchronous and synchronous communication lead to a suggested best approach. Use synchronous communication for public interfaces and asynchronous communication for internal event-driven architectures. Within an event streaming system, messages are published by producers and received by consumers. Producers publish messages to a topic or queue, terms which we will use synonymously in this context. A topic may have more than one producer, allowing producers to send messages simultaneously in parallel. Once received by the event streaming system, messages are saved to persistent storage. In the case of Oracle Database, the message is inserted to a partitioned table with an offset assigned. To receive messages, consumers subscribe to topics and read messages from those topics, typically using a polling mechanism. A topic may have more than one consumer, allowing parallel consumption of events. Within the event streaming system, end-to-end communication is asynchronous. Producers do not block for consumers, and consumers do not block for producers. When developing durable event streaming microservices, it can be challenging to ensure data consistency across multiple services due to several common problems. In the event of a process or network failure, data may be lost, corrupted, or saved incorrectly. Additionally, features like backup, restore, and disaster recovery can further complicate data consistency. Applications also often need to perform database operations at the same time as sending and receiving messages. When database operations, like inserts or updates, are combined with sending and receiving messages, care must be taken if either action fails, perform the corresponding rollback operation, to ensure no data is lost or corrupted. This is known as the two-phase commit problem and is typically solved through something known as the transactional outbox pattern, which can be complex to implement. The consequence of failing to implement these techniques can result in increasingly costly data diversions. Transactional event queues solves these problems by leveraging Oracle databases' durable table architecture and transactional messaging to help difficult, error-prone applications move to easy, reliable apps. So how does transactional event queues make developing microservices easier? When producers or consumers send or receive messages, these message operations are handled with atomic database transactions. The use of transactions in exactly one semantics allows developers to combine database operations like inserts or updates with message operations, completely avoiding the two-phase commit problem. Features like security, backup, recovery, and partitioning of message data are all provided by the database using a familiar architecture. Common paradigms in event streaming like dead letter queues can be handled through transactional event queues exception queues features, which handle expired and failed messages for consumer retry. This convergence of the event system to the database may also lower your operational overhead and network traffic by allowing you to eliminate external, costly messaging systems and leverage the Oracle database as both your relational database and event streaming system. Next, we'll look at transactions in messaging and how you can combine the two to solve the two-phase commit problem. On the producer side, the write and send of messages can be combined with database operations and committed together. In the event of an error, both can be rolled back. For the consumer, a similar process happens. When the consumer receives an event and does any database processing, the event is not received until a transaction commits. Similar to the producer, in the event of an error, both can be rolled back. These features of transactional messaging allow developers to completely eliminate the two-phase commit problem by combining DML, that is database operations, and events in single database transactions. Developers can also create chained event-driven workflows easily, receiving, processing, and sending events using atomic database transactions. Another feature of Oracle Database transactional event queues is automatic table partitioning. In many event streaming systems, ensuring consistent partitioning and replication of your data can be difficult and error-prone, sometimes requiring manual intervention. Oracle Database transactional event queues automatically performs maintenance operations behind the scenes on a topic's backing table as message volume fluctuates, repartitioning the data as necessary. Additionally, features like replication, backup, and restore are handled by familiar database controls that apply to all your data that you store in Oracle Database. Next, we'll move on to two examples using PL/SQL and the Kafka Java Clients API for Oracle Database transactional event queue. These examples will show how to produce and consume data, or enqueue and dequeue as used in the PL/SQL API. In the PL/SQL example, we'll create a new queue using the JSON payload type, enqueue a message as part of a transaction, and dequeue that message in a separate transaction. Finally, the message content will be printed to the console. This basic example can be implemented using any TxEventQ library. We'll use PL/SQL here. In this code snippet, we create a transactional event queue, setting the payload type to JSON. The payload type can be raw for binary payloads, JMS, or also an object type. The default is JMS. We also set multiple consumers to false. This allows messages to be consumed only once by a consumer. Next, we start the queue passing in the queue name. In this snippet, we enqueue a JSON message using the DBMS enqueue method. We provide the queue name, enqueue options, message properties, a JSON payload, and a handle for the message ID. To dequeue the message, we use the DBMS AQ dequeue method, using the queue name, passing dequeue options, message properties, a handle for the message payload, and a handle for the message ID. Then we print the message to the console, extracting the JSON value of the content. Now let's see this in action, enqueuing, dequeuing, and printing a message to the console. First, we create the queue and start it. Next, we enqueue the message using the JSON type. Now the message is dequeued and printed to the console, and we see message, my first message printed. Now we'll see how to perform a similar operation using the Kafka Java client for Oracle Database transactional event queues. The Kafka Java client provides a Kafka clients compatible API for transactional event queues. You can find the Kafka Java client for Oracle Database transactional event queues in the OKafka project, both on Maven Central and GitHub. This Java package is highly useful for developers who are familiar with the Kafka Clients API, as it lets them use familiar concepts with Oracle Database transactional event queues to produce and consume messages. In the Kafka Java Clients example, we'll use transactional messaging with a producer and a consumer to produce messages, run database queries, and commit or roll back transactions. Let's see how this works with the producer. This code snippet initializes a OKafka Kafka producer instance using properties with an Oracle database connection. The producer is then initialized for transactions, which should be done once after instantiation. To begin a new transaction, we call the begin transaction method on the producer. Then we send a record to a topic using the producer.send method. Next, we do some additional record processing, potentially including inserts or updates using the producer's database connection. This is the same connection that the producer uses to send the message to Oracle database. If all goes well, we use the producer to commit the transaction to the database, including whatever inserts or updates we've done, as well as the message sent. If any error occurs during our processing, we use the producer to abort the transaction, rolling back any database queries as well as the message produced. When running an example like this, we see an output that may look very familiar to a Kafka developer that uses Java. The difference here being is that the producer connects to Oracle database instead of an Apache Kafka broker. For the Kafka consumer, we create a OKafka consumer instance, similarly using props that are initialized for an Oracle database connection. The consumer then subscribes to a topic and pulls records from this topic. Using the consumer.getDB connection method, we get the current connection of the consumer that it uses to receive messages from Oracle database. For each record that we consume, we process that record, doing some database operation with the connection. If everything's gone well, we do a blocking commit with our current batch of records and any database operations that occurred in the process record method. The Oracle Database Kafka Java Clients consumer also supports asynchronous commits, whether through auto commit or the commit async method. If an error occurred during our processing, we use the database connection to roll back the transactions, both the receive of the messages and any operations that occurred in the process record method. Both the consumer and producer examples here demonstrate how developers can use transactional messaging to resolve the two-phase commit problem where data inconsistencies may arise if either the message receipt or the database operations fail. When running the consumer, this also looks very similar to a standard Apache Kafka consumer, except the connection information is instead pointing to Oracle database. Let's summarize and highlight some of the features of Oracle Database transactional event queues. Oracle Database supports persistent, high-performance queues with an in-memory cache and exactly once messaging, supporting the transactional outbox pattern. Messages are logically ordered per producer per event stream, and event routing is handled through a key-based feature or automatic round-robin routing. The dead letter queue pattern with event streaming is supported through transactional event queues exception queues, which handle failed or expired messages. If you happen to be using Oracle Database Advanced Queuing, also known as Classic Queues, you may use the DBMS AQ MIG tool package to migrate your queues to Oracle Database transactional event queues and take advantage of the newer features. From the client side, there are a variety of ways to connect to transactional event queues, including the PL/SQL API. Transactional event queues supports JMS through a standard Java messaging implementation, the Kafka Java client, which was already shown, as well as Kafka connectors, Spring integration through the Spring Cloud Stream project, as well as Spring JMS is supported, and Kafka-like REST APIs are available in ORDS. Packages in languages like Python, C#, C, C++, and others are also available to facilitate working with Oracle Database Transactional Event Queues. Finally, Oracle Database Transactional Event Queues take advantage of the converged database architecture, letting you move and hold your data all in one place and eliminate the need for external, potentially costly event streaming systems. Transactional event queues take full advantage of Oracle Database's enterprise-grade security and high availability with features like RAC. Transactional event queues also works well with Spring Boot if you're a Spring Boot user. The Spring Cloud Stream Binder for Oracle Database Transactional Event Queues combines the power of Oracle Database's event streaming system with Spring Cloud Stream's functional event-driven development model. If you're a user of JMS, Oracle Database Transactional Event Queues integrates seamlessly with Spring JMS, allowing you to use Spring's idiomatic JMS APIs like JMS Template and JMS Listener to produce and consume messages. If you're looking to get started with Oracle Database Transactional Event Queues, the Transactional Event Queue Developer Guide contains code samples for a variety of languages and APIs, monitoring and observability features with the Oracle Database Exporter, performance tuning tips, and migration features from advanced queuing to transactional event queues. Sample applications can be found in the Spring Cloud Oracle repository for our Spring JMS, Spring Cloud Stream Binder, and the Kafka Java client for Oracle Database Transactional Event Queues. You may also refer to the official Oracle documentation for transactional event queues to learn more. Thanks for watching. I hope you found this useful, and please reach out with any questions or comments you might have.